Yeah, hello everyone. I am Sipo, and this is Advanced Digital System Designs. And today we'll be talking about reliability. Um, but before I proceed, I want to give credit to Professor Redwood Sawyer, for this material, and we shall continue. Um, Today we are talking about reliability. Uh, as engineers, as people that can design systems, you need to know how reliable your system is, and because it is very important. Uh, by way of starting, we say reliability is the probability of the survival of component in an electronic system or subsystem. You see, within a given period of time, you observe your system or your component, and see how likely it is to fail, or I mean how reliable the system is within a certain period of time, within a specified period of time. This is what we refer to as reliability. And mind you, it is probability. When we talk of reliability, we talk of probability. You see, now we shall derive relationship between this reliability and then the failure rate. Failure rate is how fast the system can fail, how often the system can fail. And then as if we scroll down a little bit, we will now go to our derivation. But before that, let us make some assumptions here. We shall consider n as the total number of components. Having said that, now let us consider s of t as the number of components that will survive within a specified period of time, a period of observation. And also let f of t be the ones that failed, the number of components that failed. Okay, now we define the reliability as the number of components that survive within that time over the total number of components. That is our reliability. Now our unreliability, which is q of t, as you already know now, is the number that failed upon the total number of components. So I've established this fact. Now from basic mathematics, we know that according to these assumptions made, the total number that survive added to the total number that fail will now give us what? The total number of components. In the same vein, the reliability plus the unreliability should be equal to 1, because when we are talking of reliability, probability, from our basic mathematics, we know that probability is always, it is either equal to or less than 1. So now when we add the reliability and the unreliability, it should always be equal to 1. Now let's analyze the failure rate, and then the failure rate is now given by z of t. It is given by z of t. Give me a moment, let me get rid of these ones. Our failure rate, which is also known as the hazard rate, is given by this. which is what? Z of t equal to 1 of t, but it is the number of failure per unit time. It's the number of failure per unit time, which is also differentiating the number of failures per unit time compared with the number of surviving components, which is as this part of the equation. So this all here is for our failure rate or hazard rate. Now we shall continue with this derivation from this point, but I want to draw your attention from this very moment to something here. This is what we call the bathtub curve. The bathtub curve is so because it resembles a bathtub. Now it has three strategic or three important parts that we need to consider. First of all, we have this side of it, which is known as the early life period, and then we have this other side, which is known as the useful life period, and then we have this another area that is known as the wear out period. You see, the early life period is when you subject when you buy your components, when you buy the components from, because normally when engineers design, they normally buy in bulk the components. For instance, when you buy bulk of diodes, there could be defective diodes within that bulky component, and so you need to run a sample, a test to those diodes in order for you to weed out the ones that are defective. You see, of course you cannot test all of them during your purchase. Yes, you will do a random test on them, a sampling test, but not each and every one of them. And so it is possible that you have defective components within your component. And now in this area is where that we call the early life period, is where we subject the component to a runtime initially, and this is also known as the burning period. It's also known as the burning period, where initially you subject it to a runtime to identify the manufacturer's defective component, and when you identify them, you remove them, and thereby reducing the failure rate. That is why at this point the failure rate, by the way, this curve is a function of the failure rate and the time. And so now, after the early life period, after subjecting it, we now come to the useful life period. The useful life period, give me a second. A useful life period, which is the middle or the center part of the bathtub curve. It is the center part of the bathtub curve, the useful life period. That is from this point to this point. During that time, during the normal period, operating period, it is referred to as the useful life, and here the failure rate is constant. The failure rate here is constant. That is the useful life period, and then the status is maintained for a very long period of time. After that, we now move on to what we know as the wear out period, wherein the failure rate now increase exponentially, the wear out period. But what we should not forget about is this region, the useful life period, wherein the failure rate is constant. Having known that the failure rate is constant in the useful life period, we now return to our derivation. Now let the failure rate be constant, which is equal to lambda. If it is constant and equal to lambda, hence our reliability, which initially we define as S of t upon n, that is to say the number of components that survive upon the total number of components. Now this number of components that survive can also be expressed as this, which is n minus f of t upon n. It's just like saying if here to here is 5, and then from here, let's say from here to here is 3, which means from here to here now, which means from here to here is this 5 minus 3, which means it's 2. This is the simple logic we are using here. So which means the total the number that survive is equal to the total number of components minus the ones that fail. Going through that calculation, that's mathematics, will end up having this. And then we now have r of t equal to 1 minus f of t upon n, and so we differentiate with respect to t. After differentiating, we arrive at this point. And again, furthermore, doing our normal calculation, making the f of t over dt, which is the differentiating the number of components that fail with respect to time, making it the subject, we now have this on the other side of the equation. And we now come to the point of substituting equation 1.6, which is this one, and equation 1.7, which is this final one, into 1.5 that we had up here, this equation 1.5, the failure rate. And then after substituting, this is what we have. Excuse me for a moment, let me just get rid of these ones. Yeah, we now have this one, that what our z, our lambda, is now equal to this equation, having substituted 1.6 on 1.7 to 1.5. Now mind you, our reliability r of t is equal to s of t upon n. Now but watch this one, this part of it. It's like the reciprocal. Instead of s of t upon n, we are having n upon s of t, which means this part of the equation is the same as 1 upon reliability, the reciprocal. And this is what we are having here. You see, very basic manipulation there. And then we now come down to these points. Give me a moment, please. And then we now move on to this point, noting, so we have this, we want to do this basic integration, taking limits from 0 to t, and then we want to do this integration, substituting. We now have this one, minus log of e r of t, and then 1 to r of t. So simplifying further, we obtain r of t is equal to exponential of minus lambda t. This is what we end up having. And so this is the relationship we are trying to have, the relationship between the reliability and then the failure rate. This is the relationship. Now mind you, be mindful that the failure rate, the relationship between the reliability and failure rate is given as r of t is equal to a to the power minus lambda t. It's usually expressed as percentage failure per 1000 hours. It's always per 1000 hours. And then Euler's formula and all, we have this manipulating this one, this exponent, we have this one. Now for lambda t, for a very small lambda t, that is lambda t less than 0.02, we can write our r of t equal to 1 minus lambda t, instead of this guy here. Instead of this, if we have small lambda t, we just can truncate it to this point. And then let's move further. So this is what I was saying, that we can truncate it, and that is for the individual. Now if we are finding overall failure rate, this is what we use, this is the formula we use, finding the overall failure rate of the system. Give me a second. I hope we are following. I hope we are learning something here. And now let's look at another parameter, which is known as the MTBF, or the mean time between failure. Now when you subject your system to a runtime period, it will run for a certain period of time and then it will just fail. Yes, and then you do some repairs and then the system is back on, and then it will also run for some certain amount of time and then it will fail. And that is what we refer to as the mean time. Finding the mean of all those time it took is what we refer to as the mean time between failure. So it is just the average time a system will run or operate before it fails. That is it. So it is given by the integral of the reliability, that is the area under the reliability curve. Now when we solve that one, of course we know that the reliability is equal to exponent of minus lambda t, and then when we solve, we end up having this, which means the mean time between failure is equal to 1 upon the failure rate. That is the reciprocal of the failure rate. That is the mean time between failure. It is given by hours, since the failure rate is measured in hours, and then the MTBF is also measured in hours. It is getting too long now, and then I think we will stop here for now, and then when we come next time, we're going to go through some examples, and then we understand the topic precisely very well. We have something to deal with also. So that is it for now. Please make sure you subscribe, and then when we upload other videos, you have it right then. Till we meet in the next session. Bye. Yeah.